let's go spend a couple minutes investigating this work expression in a little more detail. I think it's pretty clear here if you think about this. You can take the amount of force that's in the direction of the displacement and multiply that by the displacement, and you get the work done. So that's the way I explained it in this derivation. The amount of force that's in the direction of the displacement times the displacement. Notice that these two vector components happen to be at 0 degrees to one another, don't they? They're in the same direction. And think about what the definition of this product, this dot product is. It's magnitude times cosine of angle between. If the two vectors are in the same direction, the angle between them is 0 degrees. Cosine of 0 degrees we know is 1. So you get positive work done. These magnitudes are positive. Now, what happens if the component of the force and the displacement are opposing one another? Opposing one another. In other words, let's say the force is this way. Let's say somebody's pulling on my arm. Somebody's pulling on my arm in that direction, to your right. But I'm physically backing up this way. How much work is done?
Negative.
My displacement is this direction. The force is that direction. So the angle between them is 180 degrees. So the cosine of 180 degrees is -1. And so this product turns out to be negative. So positive work is where the displacement, the component of the force is in the same direction as the displacement. Negative work is done if they oppose one another. That's important. All you have to do is do the math to confirm that. Okay. Now, here's a simple illustration. If I apply a force F and I allow a displacement x to occur here, or let's call it dx, then that work done is going to be equal to that force times dx. And that, moving over a differential displacement, that would be a differential amount of work. Be a differential amount of work done. Which is what F dot dr is. That's what F dot dr is a differential, right here, this is a differential amount of work performed. Okay. Let's imagine that we are in a gravitational field, since we do a lot of engineering near the Earth's surface. And let's imagine that we have an object and we want to do some work to it by lifting it up or pushing it up. So if we establish this, and let's say it was at some initial height h1, and we're going to move it up here to some height h2 under the action of some force. Then the work done to the object in raising it up against gravity is going to have to be, and why don't we call this force mg? We're not going to accelerate it. We're just going to move it slowly. Okay? So the work done in moving from h1 to h2 is going to be equal to mg times h2 minus h1. And if h2 is greater than h1, then this will be positive. This is greater than 0 if h2 is greater than h1.
So you can say a positive amount of work was done on the object?
That's correct. A positive amount of work was done to the object in moving it from h1 to h2. Carry your dynamics book up to the top of the roof. You reach out over the edge, let go of the book. What force is acting on the particle when you reach out over the edge off the top of the roof? Mg, and then what does it do as it falls? It does positive work. Gravity does positive work to the object. What does that impart to the object? Initially, it had no velocity. I let it go. It took that energy, and that energy that we had stored into it, by lifting it up onto the roof, we then hold the book out over the edge and let it go. And what it does is it gives up that stored energy and increases its potential energy kinetic energy from 0 to whatever dynamic or kinetic energy it has, the energy of its motion, as it picks up speed in the falling process.
My question on this example is the force of gravity is definitely down,
Yeah.
H1 to H2. And we are moving it against that force.
Right.
And we're calling that, in this case, a positive amount of work done. But when you were having your arm pulled by your imaginary friend, you said, well, I moved opposite the direction of the applied force. And
Yes.
you call that a negative amount of energy.
But I was talking about the work done by that person pulling on my arm.
Oh,
The work done by that person pulling on me, the particle, was negative, because that force they were applying was that direction while I was backing up away from that force. You have to be very careful in that wording. The work done by the force acting on the mass. Okay?
Yeah, just what Daniel was saying, that's why the potential energy is actually defined as the negative of the work.
Yeah, and I'm sorry I even mentioned that word. Let me retract that from the testimony or whatever, okay? From the record. I don't want to use the word potential yet. Probably by Thursday or next Tuesday class, we'll do that. Okay. And you've all had some exposure to this stuff before. So anyway, at this point in time, we want to start working problems this way, where this is the work done by the unbalanced forces acting on the mass, and it's equal to the energy of its motion, the change in the kinetic energy that occurs. You know, there's one more thing before we actually start working some problems, is we should look at springs. And the simplest type of spring to look at is a linear spring. So let's take a peek at that. If we take a spring has some stiffness associated with it, we'll call it K, and it has some undistorted length L naught. Undistorted length L naught. Now, if we start loading this spring up with some force, so what I'm going to do now is we're going to apply some force, and we'll measure X from right here. Now, X is going to then be the distortion that has occurred in the spring. And this is a real important point. The distortion that's occurred in the spring. So now, if I monitor how F, or the F necessary to cause this distortion, and this is what the book uses, is X. You know what I would use if I wrote this book? I would call that delta, because to me that implies change in length. And I think more clearly about this as being distortion than I do that. Just keep that in mind, okay? And you'll see me use both. Okay? If we start plotting, grab hold of the spring and start monitoring F's reading, the amount of forces reading, and the displacement that's occurred, as I let that displacement grow, then what would you see? What kind of a graph over here? If this is a linear spring.
Force proportion.
Linear implies straight line. So we could get something with a certain slope here. Now, if it had some slope, say like this, that would take a certain amount of force to cause a distortion, right? X1 and F1. The slope right there would be the ratio of this, wouldn't it? F1 divided by X1. F1 divided by X1. And then if I took it and let's say I stretched it a little more out here to X2, then it's going to take a proportional amount more force to cause it to get out there to X2, isn't it? X2, okay. The slope you see right here is K, that you've seen in physics. The slope is K. The units of that in the metric system typically are newtons for force and displacement, say, in meters. And so the slope here would be newtons per meter, or excuse me, the slope and the stiffness would be newtons per meter. And if the spring was linear, this would be a constant value. If I distort it 1 centimeter, there would be a certain force required to do that depending on its stiffness value. What if this slope was real steep compared to that? What would you say about the spring? Stiff. A stiff spring. In other words, it would take a dramatically more force up here at this level to cause this distortion than it would on this less stiff spring. So the slope on that relationship is what this spring stiffness is. So if we knew the spring stiffness, then the required force would be, that stiffness is nothing more than proportionality factor, isn't it? Times the distortion. So this is the spring force. Well, this is actually the force acting on the spring to create the distortion. This is the force acting on the spring to create distortion. X. So, let's do a calculation now to see how much work. Let's see how much work is done in letting it distort from X1 to X2. So we know that force dotted with dr in its general sense is the work done. So if we apply the, now, what I want to be real careful here. I want this force to be the force. You know what I'm going to do? I'm going to look in the book to make sure I get the wording the way that we want it to be. Let me think about that for a second. Yes, I want to look in the book. So what I want to do is, now let's see, I'm looking for a specific spot so I can point this out to you in the book and you can mark it because it's pretty important. Let me go ahead and put this up here in the overhead and we can look at this together. Okay, work associated, this is on page 159. Work associated with a spring force. Work associated with a spring force. We consider here the common linear spring of stiffness K where the force required to stretch or compress the spring is proportional to the deformation X, as shown in a figure. It's on the next page. We wish to determine the work on the body by the spring force. So this is important. Determine the work done on the body by the spring force as the body undergoes an arbitrary displacement from position x1 to x2. That's the piece I was looking for. The work done on the body by the spring force as it undergoes the displacement from x1 to x2. So, if we have our x1 position here and x2 position out here, and the original length was measured from here, so here's x1, and here's x2, and the wording there again, the work done by the spring, by the spring. So now, what way is that spring force? It's pointing back this way. So we have the force by the spring exerted this direction, and the displacement I am allowing to occur is in a dx direction this way. So keep in mind we have these, the force opposing dx, and I want to be real careful about that. So I have minus kx is the spring force, and I could go ahead and use the unit vectors like they did in the book, I hat, and I'm dotting that with dx, and I'm integrating that from x1 to x2. You all with me? We're talking about what the spring is doing to the mass. What the spring is doing to the mass. So now, when we integrate this, these, oh, I'm sorry, dx I hat. Had to be careful there. These have to be vectors. Vector, vector. Now, I hat dotted with I hat. I hat dotted with I hat is 1. Cosine of 0 degrees is 1. So that's 1. And so what we end up with is minus 1/2 k x squared between x1 and x2. And so we get the work done is equal to negative 1/2 k x2 squared minus x1 squared. So what you notice here, if x2 is greater than x1, then this work done by the spring acting on the mass is negative. And back over here on this picture, if you think about what we were just doing, here is your differential element that we just built. The differential element that we just built. And here is the kx force. Here is dx. And we integrated that from x1 to x2. And that turns out to be the area, the negative of the area underneath that trapezoid. the negative of the area under that trapezoid.